Welcome to In 5 Minutes. Let us do a similar mathematical analysis, this time for another type of angle modulation, which is called frequency modulation. I'm going to consider a modulated signal once again. Please note that the carrier signal is Vc cos omega ct with the original carrier frequency of Fc and the original phase angle of 0. The modulated signal that I'm going to consider now is Vc cos omega ct plus k dash mit. You can once again see that the phase of the modulated signal that I've considered does not remain constant. The phase is changing, but the amplitude is kept constant. The amplitude of the original carrier signal is kept constant to the peak amplitude equal to Vc. So let us see what kind of modulated signal this turns out to be. I can only understand the nature of the signal if I can define MIT that I've taken. So here MIT is nothing but I stands for integration, M of t is my modulating signal. So MIT is nothing but integration of the modulating signal. Modulating signal is M of t. If I integrate M of t, inside the integration I'll use a dummy variable. So it becomes M of tau d tau. And mathematically integration is defined starting from minus infinity to any present time instant t. Integrator when takes the input m of t. So how do you generate this signal? So we will need an integrator block. Integrator block takes in m of t, which is the modulating signal, and its output will be nothing but mit. Every integrator block will have some time constant, so I'll just mention that constant in the form of k double dash. So if I put this expression back into my modulated signal that I've considered, it becomes Vc cos omega ct plus we have k dash and we will have k double dash of mit. I replace k dash k double dash with a constant 2 pi kf. So we will discuss why we have extra 2 pi here and what is the significance of kf later on. So we right now replace k dash and k double dash with k pi 2f and we get integration expression of the modulating signal, which is integration m tau d tau from minus infinity to t. Now let us try to understand what is happening to the frequency of the signal. We have already defined the phase of the signal. So you can see that the phase of the signal phi of t is directly proportional to the integration of modulating signal. This is definitely not phase modulated signal, because in phase modulated signal the phase will be directly proportional to the modulating signal. After understanding the nature of phase, let us find out what is the frequency of the signal. The instantaneous frequency omega can be found by differentiating the total angle of the sinusoidal signal. The total angle in this case is omega ct plus 2 pi kf integration m of tau d tau, where the limits of integration are from minus infinity to t. If you differentiate this, we get omega equal to derivative of omega ct will be omega c plus the derivative of the remaining part will be 2 pi kf. It's a constant, it will remain as it is. Derivative and integration both will cancel out each other and I'll get back my original m of t, which was being integrated otherwise. So I get my original m of t, which was being integrated otherwise. So that's my instantaneous frequency in terms of radians per second. If I divide throughout by pi, I'll get omega by 2 pi equal, if I divide throughout by 2 pi, I'll get omega by 2 pi equal to f. Omega c by 2 pi will be carrier frequency fc. 2 pi is already there here, so it will cancel out. We'll get kf into m of t. So if you now observe carefully, the instantaneous frequency of the modulated signal that we have considered does not remain constant, but it is equal to kf times m of t, where kf is a constant, and that means frequency, the instantaneous frequency around fc, the original carrier frequency, is proportional to the modulating signal. And as per the definition, because frequency is proportional to the modulating signal amplitude, what we get is frequency modulation. So the signal that we had considered, in which the phase was proportional to the integration of modulating signal, turns out to be a frequency modulation.